Come on, George. All right. Okay, so we're trying to prove that if A, B, C, and D, E, F are perspective about the line X, Y, Z, okay, this diagram's a bit messy, but whatever. Um, and that if that and we know that if they're not coplanar, they're perspective about a point, okay, for any two triangles like that. And we're trying to prove that if they are coplanar, then they're also perspective about a point. Okay. All right. And this is definitely the problem-solving approach to proving this. It's probably not the write-up. Okay. But basically, we're trying to mimic the forward direction. So this is the main motivation, and that's why the letters of the points are named S, T, A prime, and G prime, to mimic the things in the forward direction. Okay. Okay, so what are we doing? Okay, so we got everything's on one plane to start with. Okay, including X, Y, and Z. And so we want to use the three-dimensional result, so we want to get out of the plane, right? So we define G to be any point outside of the plane. Yeah?
Yeah.
And I guess because it's any point, you can kind of move it a little bit if you run into some coplanar problems later, yeah?
Yeah.
Okay, so you're kind of free to move G. Okay, and then we define um so then we define T to be any point on GY, yeah? Yes?
Yeah.
And we define S to be the intersection of GY and TX, yeah?
Yeah.
And this is to mimic the part of the proof before where XST are collinear and they project onto XYZ from G, right? Okay. Okay, so now this is a bit weirder because now we have um so now we have a triangle called GST, okay? And we don't like the GST, but where we have to deal with the GST, and its perspective with with ABC, it's about the line XYZ, okay, which we call L, and it's also perspective. If you're gonna do ABC, you might as well do DEF, right? So it's also perspective with DEF, and it's somewhat by design, okay. Okay, and also it is also outside of the plane of those triangles, okay. So then the converse of Desargues for non-coplanar triangles applies. Yes? Okay. And so when we apply it to ABC, we get this point which we um, sort of affectionately call it G prime. And when we apply it to DEF, we get a point which we call A prime. Yeah? Okay. So, yeah. And just to kind of catch you up, obviously G prime is the intersection of BS, AG, and CT, and A prime is the intersection of TF, GD, and ES. Okay. All right. Now, now, so by design, I guess, because S, if you look at the other proof here, okay, we have basically put triangles perspective from a point, a perspective about the line, but in our case, we have all these lines already from our design, right? XST is a line already. So, which means that A prime EF and G prime BC are perspective about a line, okay? Um, and if they're not coplanar, then that means they're perspective about a point, right? So can we quickly check that they're not coplanar? So let's see, A prime EF, EF, and G prime BC. Yeah. I mean, if they're coplanar, I guess G prime would be coplanar with BCEF, right?
But
But
it's
but it's not.
because G because it's AG.
Yeah. So so we can kind of be comfortable that even if they are coplanar, we could just kind of tweak it a little, but they're not. Yeah. So the perspective about a point. Okay. And so this point is the intersection of A prime G prime. Yeah. So maybe we can call this point P1 or something. Yeah. So we can call this point P1. P1, right? It's the intersection of A prime G prime with EB, so BE, and also with CF. Okay, so this is this thing here. Okay, so this is P1 in particular, A prime G prime there. Yeah. Okay. If we notice that GSZ is collinear, GSZ, yes, by definition, basically. Yeah. We get this thing as well from the previous proof. But you don't need the motivation to verify that it works. So A prime, so now again we have another point P2. I'll write in red now. P2 is again A prime G prime intersect, but now it's DAD and BE, yeah? Yeah? And AD and BE, so this is P2, yeah? Okay. And obviously you can do the same thing, you get P3, but I think we already have enough with P1 and P2, is that right? Because P1 and P2 are already A prime G prime intersect BE, yeah? So they're already the same point now, yeah?
Yeah.
So P1 equals P2, right? And so you actually have all three things equal to a P, which is the conclusion of the statement, right? Right. Okay. Do you think, like, the only thing that bothers me, I mean, this is actually pretty good because you kind of use everything in like, we use everything, right?
Yeah.
The thing that bothers me a little bit is its relationship to the forwards direction. Yeah.
Well, what do you mean relationship?
Like, it kind of bothers me that I don't have quite a very clear expectation of what the relationship should be, and despite that, I feel like I'm a little bit surprised. This is what the converse looks like given what the forward direction is. So maybe, do you think this is like, is this proof an analogy of the forward direction proof, or is it like it's almost like it assumes the forward direction proof, like kind of a different relationship? It's the backwards proof.
That's like, yeah. Like, to be fair, how would you think of the forwards direction? You make an arbitrary point. I don't know.
So now, if you had this was the original proof, right?
Yeah.
How would you do the
just
forwards
go backwards.
direction?
Yeah.
You just do this backwards, right?
Yeah.
That doesn't make sense, does it?
That's the motivation. And then we can keep them like.
The G prime is any point on AG.
Yeah.
A prime is the intersection of, what is it? G, D, and
Intersection of something.
yeah. Yeah, so there's a lot to learn in maths just beyond even like it's hard enough to understand why the theorem is true, but there's all these other expectations too, isn't there?